And we are live. Yes, this is Liverpool, one of my favorites. And there's this dog. This is Mocha. Now, she's full grown, but she's not very big, as you can see. Not long ago, I saw another dog that looked exactly like her. It even had the white mitten on one front paw. It was identical to her, except the dog was a lot bigger. And I thought, wait, if that dog had puppies, maybe a little puppy that's just a few weeks old would look like Mocha. That would be really cool and interesting. But I like Mocha the way she is. What I could say is Mocha was very similar to that other dog. Okay, lie down. That's right. Stay. Go to sleep. Similar, yes. So Mocha is small, and she's similar to this other shaggy brown dog that's bigger. It's as if you could take Mocha and just sort of stretch her out, and she would be that big dog. And that's kind of what we're doing this week in our geometry with Doug and Dog, mostly Doug, lesson. We are talking about the idea of similar shapes, similar triangles, for instance, but it doesn't only work with triangles. Similar shapes have the same angles and proportional sides. So I have an example right here. I'm going to erase this soon. I'm going to need to make room, but I have an example. Here's my original shape. And it's small, kind of like Mocha. We could say that the length of the three sides are 3 inches, 4 inches, 5 inches. I drew them a little bigger, but they are drawn to scale. And then we have this other triangle, which looks like the same triangle except for its size. This is my new one. Okay, so if I were to take Mocha and stretch her bigger into that other dog, well, it's the same sort of thing as if I were to take this triangle and stretch it bigger so that it becomes this triangle. We start with the original smaller one and we end up with the new bigger one. But of course, we don't only have to shrink a shape to get another similar shape. We could also have an original shape that's big, and then it could shrink down into a new shape that's smaller. And all of these are ways to visualize what we mean when we talk about similar shapes. I'm going to erase this little definition to make a bit of room, and now we're going to start playing around with these two triangles. Now, you might recognize these triangles if you were here for my lesson just a few weeks ago when I was teaching Pythagoras' theorem. I was introducing some of my favorite triangles. I like to call them magic triangles or something like that, because this is one of them, this 3, 4, 5 right triangle. And this other one, I used both of these in that lesson. They're very useful because when you're teaching Pythagoras' theorem, when you do the calculations with these triangles, you don't get all sorts of decimals in your calculator, especially after pressing the square root button. And that makes them really good for teaching students how Pythagoras' theorem works, because these triangles really do work for Pythagoras' theorem, but they work with nice whole numbers, and you don't have all sorts of decimals. That means that the student who's learning Pythagoras' theorem isn't distracted by all the decimals, and they can see what's going on in it. These are good triangles to start people off with. But they're also good triangles for what we're doing right now. So, there's something that determines how much bigger this original triangle had to get in order to turn into this new triangle. And that thing is called the scale factor. We'll just call it SF, but I'll write it here. Scale factor. And we'll refer to that as SF for short. And the scale factor is a number. It's the number that we have to multiply each of these side lengths with in order to get the answer to be these side lengths. And for this to work, it has to work for all of the side lengths in the two triangles. If I multiply, for instance, if I multiply 3 by 2, I get 6. So, okay, this 3 is being multiplied by 2 to get that 6. But if the two triangles are really similar, then it means I also have to be able to multiply this 4 by 2 to get this 8. And you can see that that's going to work. And I have to multiply the 5 by 2 to to get the 10. That has to work. It has to work for all of the distances in the triangle. The 3 side lengths are 3 of the distances, but it even works for the perimeter, which is also a distance. What's the perimeter of this one? 3 plus 4 plus 5 equals 14. No, it doesn't. It equals 14. How did I get 14? It equals 12. 3 plus 4 plus 5 equals 12. I'm going too fast, Doug. What about this one? 6 plus 8, that's 14, plus 10 equals 24. Oh, so the scale factor is applying to everything. 3 times 2 gives the 6, 4 times 2 gives the 8, 5 times 2 gives the 10, and even the 12 perimeter, that one, messy, times 2 gives the 24 perimeter for this one. It's working for all of the things that we measure with a ruler with these 2 triangles. And the cool thing about similarity is it doesn't only work with triangles, it works with all sorts of shapes. And we will get to some more shapes eventually in this lesson. Now, how do I apply the scale factor? How do I think, well, what's the scale factor here? Well, I think we kind of know what the scale factor is. The scale factor is this too. We keep on having to multiply the original by 2 to get the new. So we can express that by putting new over original. In this case, for example, 10, that's the hypotenuse of the new, over 5, which is the hypotenuse of the original. And of course, 10 over 5 reduces to 2 over 1, or 2. Of course, when a fraction is over 1, you don't have to express it as a fraction anymore. We can express it as a whole number. But being able to express it as a fraction is actually really useful with this type of math, where most of the time I would say, okay, yes, 10 over 5, that means my answer is 2. I like in this similarity math to say my answer is 2 over 1, because it describes a 2 to 1 ratio between the sizes, the distances in the new versus the original. Having both numbers there to see the 2 and the 1 kind of makes it really clear. Okay, what is it I wanted to do next? I want to point out something. I'm going to erase some of this stuff. I want to point out something that makes this work so well, and it's not a coincidence which sides I'm choosing when I show these relationships. I'll even erase these perimeters. I don't really need any of that anymore right now. When I compare the 2 triangles, and I'm trying to, for instance, to figure out what the scale factor is, it's important that if I'm talking about this side that's 3 inches long, I'm going to pair it with the side from the other triangle. It's important that I choose the 6. Why? Because the 3 is the smallest side in this triangle. I have to put the smallest with the smallest for this to work. So, new on top, my 6 is the smallest over my 3, which is the smallest. And that has to be equal to, how about the medium-sized ones? The 8, which is the medium size in the new, over the 4, which is the medium size in the original. And that, of course, also should be equal to the relationship between the 2 hypotenuses. The 10, which is the largest size. I use hypotenuse because, let's face it, it's a right triangle. So yes, that is a hypotenuse. But I also want to point out it's also the largest side. And we know that the hypotenuse is always the longest side in a triangle when you have a right triangle. So the 10 is the longest over the 5, which is the longest. So this is smallest over smallest, must be equal to medium over medium, which must be equal to longest over longest. And I'm always putting the new on top. All of these things are necessary to make this work. I can't just grab any 2 numbers and put them together and expect it to equal 2. These ones are all equaling 2. If I reduce these 3 fractions, this reduces to 2 over 1. This reduces to 2 over 1. And this reduces to 2 over 1. When you make that happen, you're proving that the 2 triangles have to be similar. Okay, Mocha. Okay, enough. Sorry, the dog is making some weird noises. Now, we are able to find a scale factor that way because we're following some rules. Smallest over smallest, largest over largest, etc. If I were to take the 5 and put that on the bottom, but put the 6 on the top, well, this is not going to turn into 2 over 1. It's not working because I'm not following those rules. So if I want to put a side from each triangle together and have it show me the scale factor, I have to put smallest with smallest, or medium with medium, or largest with largest. Okay, let's do another example, which means I have to erase these gorgeous, beautiful triangles that I drew. But I will draw some more. And for now, we're going to stick with right triangles because I find they're a nice, easy type of shape to start with when we are just starting the similarity concept. So now I'm going to draw 2 of them, but notice how with my first 2 triangles, I gave all the side lengths. And then we're able to figure out the scale factor. But that's not the only way you do this type of math. One of the ways you do this type of math is you get some of the side lengths but not others. And you figure out the scale factor and you use it to help you figure out the missing side lengths. And that's what we're going to start doing. So my original is actually very big. Let's see here. Do I want to do the whole thing? How long is that? I think I'm just going to make this side, like make sure this fits. I'm walking off camera, but I want to make sure the triangle side stays on camera. I'm drawing a 12-inch side over here. So that's 12 inches. I'll label it. And then I'm going to draw a right angle, and I'm going to put a 16-inch long side. So I'm using another one of my magic right triangles. 16-inch perpendicular side, therefore it forms a right angle. And then I'm going to connect the 2. I'm drawing my hypotenuse. And that is going to be 20 inches in length. And if it were a Pythagoras lesson, I would be calculating it and proving it. But we already know this is 16 inches. And this is 20 inches. There. That's going to be my original. I'll just write orig. And then over here I'm going to draw my new, which is going to be a little smaller. I'm going to draw an upright side, which is 9 inches. There's my 9. And then a perpendicular side to that, which is going to, I'm not going to say how long it is. But I'm going to draw it, show that it is a right angle, and then connect the 2 with the hypotenuse. So you can see that the new, which is here, is smaller than the original. The new doesn't have to be bigger, not every time. I did that with the first example, and now I'm doing the opposite with the second example. This time the original is bigger than the new. And what side length do we know? We know that this side here is 9 inches. But I want to find this side, which I'll call A, and I'm going to find this hypotenuse, this side, which I'm just going to call B. No, you know what? I don't want to use B. I'm going to use X and Y. Y. Of course, it's a variable. I can use any variable I want, really. Okay, so now we want to find the scale factor again, like we did the first time, but we also want to figure out how long is this medium length side and how long is this longest side. Using those words helps us to figure out what to do in the new triangle. So the scale factor. The scale factor has to be equal to the length of the shortest side in the new over the length of the shortest side here in the original, which is 12. So we're putting the 9 and the 12 together, and we know that's the right thing to do because they're both the shortest side lengths in the two triangles. So this is my scale factor. My scale factor is 9 over 12, which as usual has new on top. The other one had 2 over 1. It had the bigger number on top. And this one has the smaller number on top. Does that make sense? Yes. Because if we always put new over original, then when you have an original that's smaller and a new that's bigger, then the scale factor is going to be a number larger than 1. And it was in the previous example. It was a 2. Everything got twice as big. In this one, the new is smaller than the original, so it makes sense that the scale factor is a number that is less than 1. 9/12 is less than 1. So this tells us right away that the new is going to be smaller than the original. Everything makes sense when you have a way of doing it. I can also reduce this, of course. If I divide both top and bottom by 3, I get 3/4. I get 3/4. So my scale factor is 3/4. This is now a simplified scale factor. But the thing that's kind of fun is that I can use the simplified scale factor to help me figure out the missing side lengths, but I could also use the unsimplified version to help me find the side lengths, and it would also work. So you don't have to reduce the fraction you get as your scale factor in order to be able to use it to calculate missing side lengths. That's kind of neat. In this case, in this example, I'm going to use the 9/12. I'm going to kind of prove it. 9/12 can be used in a proportion. It's a ratio, and a ratio can be used in a proportion, which is just two fractions with an equal sign in between and is solved with cross multiplication. But I have to do this twice because I'm looking for two things. So I'm actually answering two questions right now. And in both cases, I'm going to put 9/12. And now I have to figure out where to put my x and my y and these other side lengths in order to answer the question. So, for side length x, that's the medium length side, it's part of the new, so it goes on top. It's part of the smaller triangle, so it's going to go on top. So I'm putting x on the top. And then that's a medium length side, so the number I have to put on the bottom has to be the 16, the medium length side here in the original. I have set up my proportions so that I can cross multiply and find the missing side length. I'll finish it and then I'll do this other one. So cross multiplying, bottom times top equals top times bottom. 12x therefore is equal to 19. 9 times 6 is 54. That's 144. And then if I divide both sides by 12, cancel, cancel, x is isolated and it's equal to 12. It means that my side x here is 12. I've answered a question. I found a missing side length by using the scale factor and the fact that the two triangles are similar. And I use cross multiplication, which we already know how to do, and I can do it as many times as I need to. So I can do it again to find y. Y is also part of the new, so it's going to go on the top. And then it's the longest side of the new triangle. The longest side of the original triangle is 20, so the 20 goes here. We have a way of building our proportions so that the numbers and the variable end up in the right places so that we get a correct answer. Having a strategy for how you do this is important. Okay, cross multiplying 12 times y is equal to 9 times 20. 9 times 20 is 180. 12 times y equals 180. If I divide both sides by 12, these cancel. More chalk, please. And 180, y is isolated. Is that fitting on my video rectangle? Y is isolated, yes it is. 180 divided by 12 is 15. So that means y is 15. I found both missing side lengths. And I was able to do that because I knew they were similar and I knew the 9 and the 12. That gave me my scale factor. The rest is easy. So this works. It only works if the two triangles are similar. So a lot of these questions where you end up solving to find missing side lengths like this, the question will tell you the triangles are similar. Or they give you some evidence that allows you to prove that the triangles are similar. And then you go ahead and you do this. It works. And we did that with our unreduced scale factor. We got the right answers. And these should be, I should have a unit of measure. So they should both be inches because the unit of measure for the question was inches. Okay, it's time to do this again. And we'll do something that's quite similar. similar. We'll do something that works kind of the same. I don't know. We can say it's quite similar. I'm moving on to my next page. Okay. Some of these triangles, the way I chose the sizes of them, might not be as easy to draw as others and make them fit into the video and leave us room to do our calculations. But I'm just going to do my best. Okay, let's try this again. And we're still sticking with triangles. In fact, we're still sticking with right triangles for now. But this similarity stuff works for other shapes, and it works for other types of triangles as well. So long as the two triangles or the two shapes are similar, this math works. First, I'm going to take a sip of my fizzy water. Watermelon. Okay, how about this one? This is 24. Yeah, I can make this one fit. I'm going to keep on putting the original on the left, but you don't have to. You can move the original onto the right, and I keep on drawing my triangles so they're sort of pointing in the same direction. You don't have to do that either. The orientation of the shape doesn't matter when you're dealing with similarity. So it means that you can rotate the shapes any way you want, and they'll still be similar. Okay, how about my original? I'm going to start with a side length here of 15 inches. And then I'm going to draw a perpendicular side that is going to be 20 inches in length. There's 20. There it is. Show my right angle. And then I can just connect the two. Can I? Is this ruler long enough? Well, kind of have to extend it a little bit. Right here. There. Huh, okay, and I had 15 inches, 20 inches on the third side. The hypotenuse is 25 inches. And that's my original. And this one's big enough that I can write the whole word inside it. Now over here, and I'm going to prove this thing about orientation, I'm going to draw another triangle that's not oriented the same way. And it is going to have, how do I do this? I have to see what will fit. This will, I can go quite far over here with this triangle, and that's good. There. That side length is 30 inches. But I want to draw this side up here, and I'm not going to say out loud how long it is. And if you can guess, because you know my equipment really well, don't guess. No, that didn't work. Hang on. That's why it didn't work. Okay, I'm going to do this over again. And I'm going to end up redrawing that line. Actually, what I'll do is I'll just erase some of that line. So I want to make a nice 90-degree angle up here. Yeah, this is going to work. I think it's going to work. There. Yes, it's working. I need to name, I'm going to put letters for the two missing sides. I used X and Y last time. I think I'm just going to use M and N for these two. Okay, I think I'm set up. These are similar triangles. I'm saying it, they're similar. So we're going to use similarity to figure out the scale factor and to figure out the missing side lengths. And it's still going to work even though this triangle is facing a different direction than that one. You can see they're both right triangles, but two triangles are not necessarily similar just because they're both right. These are two similar right triangles, and I have to say so. So let's find the scale factor. How are we going to do this? We can see the hypotenuse of this one is 25, and oh, I should label this as new. And the hypotenuse of this one is 30. So I'm going to get my scale factor first. Scale factor is going to be new over original, so that is 30 over 25. And again, this can be reduced, so I'm going to reduce it, and the common factor between 30 and 25 is 5, so I'm going to divide by 5 over 5, and I'm getting 6 over 5. Here's my reduced scale factor. It's really the same number as this one. If you do 6 divided by 5 in the calculator, you will get 1.2. If you do 30 divided by 25 in the calculator, you will get 1.2. But I prefer using fractions instead of decimals for scale factors, because the fractions lend themselves so nicely to being able to set up your proportion and your cross multiplication. Okay, so 6 over 5 is our scale factor. And this time I'm going to use the reduced version of it into proportions in order to find side length, the length of side M and the length of side N. Okay, let's get busy doing that. For M is the shortest side in this triangle. And therefore it's going to go with the 15, which is the shortest side in this triangle. So I'll put my M, and M is new, so I'm putting it on the top. 15 is original, I'm putting it on the bottom. Cross multiplying, 5M equals 6 times 15. 6 times 15 is 90. When I divide both sides by 5, we isolate my M, and 90 divided by 5 happens to be 18, and it's 18 inches. So M equals 18 inches. And now let's find side N. N is the median length side in the new triangle, and the median length side in the original is 20. Cross multiplying, 5N equals 6 times 20. 6 times 20 is 120. Divide both sides by 5. Cancel, cancel. N is isolated. 120 divided by 5 is 24 inches. So N, will this fit? N equals 24 inches. Did it fit? Yes, it did, just barely. Okay, it works. So now we've seen that the orientation doesn't matter. So long as the two triangles are similar, it doesn't matter which way they're twirled around. And using the unreduced scale factor works, but using the reduced scale factor also works, so you actually have a choice there. I tend to want to use a reduced scale factor because it makes all the numbers a little smaller, and that makes it easier for me to avoid mistakes. That's one reason to do it. But if a student wanted to use 30 over 25 in their proportions, I wouldn't argue with them, especially if they keep on getting the right answer. One other thing we can do with this, let me take a look at that. Is, why not find the perimeter? But with the scale factor. So even though I could easily figure out the perimeters of both of these just by adding, I'm going to find the perimeter of the small one without adding. I'm going to find the perimeter of the new one by adding, and then I'm going to use it and the scale factor to find the perimeter of the original one. So the question doesn't have to ask you to figure out things that are part of the new triangle. The question can be structured so that it tells you things about the new triangle and you figure out things about the original. That works as well. A lot of things work with similarity. I'm going to erase both of these. Of course, we now know the answers. They're all written over, they're both written over here. Okay, so the perimeter of this triangle is going to be 18 plus 24 plus 30. And that will be what? 30, 54, 64, 72. 72 inches is the perimeter. Now I'm going to apply the scale factor. And I will use the reduced version, 6 over 5. The perimeter that I figured out here by adding is the perimeter of the new. So it has to go on the top. And then I can use, I guess, an X to represent the perimeter of the original. And now let's do cross multiplication. 6 times X equals 5 times 72. 5 times 72 is 360. x equals 60 inches. The perimeter of this has to be 60 inches. Should we check? 25 plus 20 plus 15. 5 plus 5 is 10, carry the 1, 2, 4, 5, 6. Yep, it works. So any of the side lengths of the smallest, medium, or largest, and even the perimeter can all be found using the scale factor if you know that the triangles are similar. I like that. Now this smallest, medium, largest thing, I want to do that over again with our first example. I'm not going to redraw the first example. I'm just going to remember the numbers that went with it. And I'm just going to write this smallest, medium, largest thing again because it's useful and it's important. If you get the sides mixed up, then you end up with all sorts of mixed up answers and it'll be hard to learn anything. So remembering that with the triangle, there's a smallest side, a medium side, and a largest side. Well, not in an equilateral triangle, but in the type of triangle that we're doing, and in a lot of triangles. So noticing which is the smallest and which is the largest side in any shape is useful when you're working with similarity. Okay, so how about I write smallest over smallest? Must be equal to medium over medium. A lot of writing. Which must be equal to longest over longest. Yes, I could have said largest here, and yes, I could have said shortest there. There's different words that will work, but the concept is what's mattering. And I want my new on top and my original on the bottom. Is that all fitting? Yes, it is. And then I try to remember what was going on with my first two triangles. The smallest side of the smaller one was 3 inches, and that was my original. And the smallest side of the larger one was 6 inches. Mediums were a 4 and an 8, and the longest were a 5 and a 10. And all of these reduce to 2 over 1. Crooked, there, that's a 1. And that's my scale factor. 2 to 1 is my scale factor. Which is a reduced version of all three of these fractions. There's a lot of overlap between the concepts of fractions and the concepts of similarity. And then this whole idea about reducing and expanding fractions, which is something we've worked on a lot in the past, also applies really well to similarity. You can see how math is always built upon the other math that you learned before. And the better you learned that other math before, the easier it is to understand the new math. Math to me is very much layers of the onion. You need those inner layers to give you a foundation upon which to build the outer layers. Okay, so I just wanted to remind us about the smallest, medium, largest thing and how it applies with our very first example. And I'm finished with this page. Okay, I think I'm finished with triangles. Or at least I'm finished with right triangles. I've used more than half of my time. I want to move on to a new type of shape because similarity doesn't only work with triangles. So I'm going to do something with rectangles now. So I'm going to draw 2 rectangles, an original and a new. And I'm going to give some of the dimensions, and then we're going to figure out the scale factor, and we're going to find any missing side lengths. Okay, first rectangle over here. I'm going to draw this fairly small one. So this side length is right there. Am I giving it? No. I'm going to just call that side length x. And then, drawing a perpendicular line, I'm going to draw another side length, which I can't see because the little red bar in the middle of the ruler is in my way. And I'm going to label the length of that side, and that is 12 inches. And now I'm just going to complete my rectangle. I'm doing it freehand, but I'm doing my best to make sure I really have right angles. And they look pretty good. I'll even draw the little right angle symbols in. So we have enough information. Because it's a rectangle, we can figure out how long this side is, and we know this is equal to the 12, and this is going to be equal to the x, whatever x is. And now we're going to do the second triangle. This one, I'm going to draw a side 9 inches long, perpendicular side, which is going to be 18 inches long. Do that again up here. And complete my rectangle. Pretty good. Okay. And I'll label it 9 inches here, 18 inches there. And again, we have all the information. We need to know everything about this rectangle and almost everything about this one. Okay, how are we going to find the scale factor? The same way we find the scale factor with triangles. I am also going to label that this I'm considering my new, and over here this is my original. Just enough room to write the word original inside this little rectangle. Do I always have to have the new on the right? No. I could really move it around. It's just convenient that I keep on putting new on the right and original on the left. It doesn't matter where they are on the page, and it doesn't matter how they're twirled around. I could rotate this 90 degrees so that the shortest side is on the bottom and the longest side is on the side, and it would still be similar to this one. The two rectangles are similar because I gave you two rectangles that are similar. Is it possible to have two rectangles that are not similar? Yes. So you have to be told they're similar, and I'm telling you right now, these two are similar. Let's find our scale factor. We're doing it the same way. We're putting new over original. We have to use the 18 over the 12 because that's the longest side in this rectangle over the longest side in this one. I can't combine the shortest side of this one with the longest side of this one. I can't do a scale factor using the shorter side of this one because I don't know it. So this is my only option for finding my scale factor. And I can reduce it. I'm going to reduce top and bottom by 6. And I get 3 over 2. I have a 3/2 or 3 over 2 scale factor for these two rectangles. And now I can use the scale factor to find the missing side length. 3 over 2 equals, get ready, draw the skeleton of your problem. Now the x is from the original, which means I'm putting it on the bottom. And the 9 inches, is from the new, that goes on the top. Cross multiply and solve. 3x equals 2 times 9, which is 18. And when I divide both sides by 3, cancel to isolate my variable, 6 inches is the length of x. Side x is 6 inches. And I can do the perimeter as well if I want. The perimeter here is equal to 2 times length plus width. I'm only doing this because it's so fast to do, which is equal to 2 times 18 plus 9, which is 2 times 27, which is 54 inches. And now if I want, I can do another proportion using the same scale factor. The 54 inches is from the new, it's going on the top. 3x equals 2 times 54, which is 108. Divide both sides by 3. What is that giving me? 108 divided by 3, 36. So x is isolated and is equal to 36 inches. 3 times 30 is 90, 3 times 6 is 18, 90 plus 18 is 108. Okay, I feel good about that. 36 inch perimeter for this thing. We know x is 6. The perimeter is equal to 2 times 12 plus 6, which is 2 times 18, which is 36. It's working. It's written a little bit messier. I'm sort of at a different angle than I'm used to. Inches, it works. We're able to use the scale factor and the perimeter of one of them to find the perimeter of the other. or we can use the scale factor to figure out the missing side length and then just directly calculate the perimeter. We have all sorts of choices in this situation. Rectangles go rather easily. Okay, now I have a really big rectangle. And I'm going to do it again, another pair of rectangles. The rectangles are not taking so long. This time I think I won't bother with the perimeter. I'm just going to find the missing side length, because I do want to move on to some other shapes, and we'll see how many of them we have time for. When the shapes are easy, the examples will go quickly. So I think I have a few kind of easy-ish ones coming up where we can make sure that the examples go quickly. But first I have to draw. Okay. Now, what did I'm trying to figure out what unit of measure I used when I drew these on my page. Yeah. No, you know what? Instead of trying to draw them life size, I'm just going to draw two rectangles, and I'm going to give the dimensions, and it's just a scale drawing. So, I have to have some ideas in my head for how I'm going to do this, see where this is. How far is this? Will it go right off of the video rectangle? We're about to find out. Ooh, came close, but no. Okay. No, I'm making it too big. I'm not, because this is the smaller one. I'm drawing the new right now, and it's the smaller one. So I'm going to make it smaller, because otherwise I won't be able to fit the bigger one over there. So I'm taking a new strategy. Oh, that's a good strategy. It's already right about the length I want. There. Okay. So this rectangle ended up quite a bit smaller. That's my new drawing strategy. Let's quickly finish it. Okay, and I'm going to label it 2 inches. You can see this is bigger than 2 inches. So it's just drawn big enough so we can see it in the video, and we have to believe the dimensions that are given with it. This is 1.5 inches. Yeah, try and make this interesting. Over here, I'm going to draw this, and I'm going to label it right away 3.75 inches. And then, will this fit now, or go off of my video rectangle? I think it's going to fit easily. We're getting two rectangles. By hook or by crook, I am managing to get them. Okay. Rectangle symbols, kind of square angle symbols. And then this, I don't want to give the other dimension. Oh, now I'm understanding what I meant to do with this example. So yes, I am going to give the other dimension. So this is 5. Because the question that we're asking now is, what is the scale factor? Because that's one of the things that can happen with similarity, is you can be given two triangles and told that they're similar, and given the scale factor, and then you can find missing side lengths with it, or you can be given two triangles that are, and told they're similar, and then you're not given the scale factor, but you're given enough information about the side lengths so that you can figure out the scale factor. So that's what we're doing right now. We have to figure out the scale factor. How is this going to go? We have some weird decimals there, but what I can do, I have to know which is new and which is original. It really means that this is two possible problems. I can can do the whole thing with this is the original, and then I could draw two rectangles the exact same sizes, but make this sized one be the new, and we have a new problem. Okay, so the scale factor is going to be new over original, which is going to be 2 over 5. 2 inches over 5 inches. And now this is already as reduced as it can be, so we have a correct scale factor. But wait, could we find the scale factor if we use these weirder looking decimal ones? Yes, we still have to put new over original, so let's try it. 1.5 over 3.75. It is the same scale factor. Both of these will work, but this one's a lot easier to look at. So this is not only reduced, it's a fraction with decimals inside it. What do I do? And there's various ways that we can approach this, but what I'm going to do is I'm going to multiply this by 4 over 4. Because I know 4 times 1.5 will give me 6, which is a nice whole number. I got rid of the decimal. And then 4 times 3.75 is going to give me 15, which is also getting rid of the decimal. Now I could have done that more with trial and error, because what if I didn't realize 4 over 4 would work? I could try doing 2 over 2, and that would expand it and get rid of the decimal on the top, but I'd still have one on the bottom, so I'd have to do it again. When we work with reducing and expanding fractions, we've gone through all of this. So it's something that we know how to do. It's something that's in our skill set, but we're not quite finished because this is not reduced. I want to reduce it. If I'm reducing this as much as I can, I'm going to divide the top and the bottom by 3. And that's going to give me 2 over 5. And now I see some nice proof that yes, indeed, this scale factor is equal to that one. So if you have a scale factor that's reduced, it's probably the best one to use. If you have one that needs to be simplified, if you simplify it, it's going to give you the same scale factor as the perfectly reduced one. So we can make sure that the numbers we have really do represent the same number. Of course, there's always a shortcut for this, isn't there? Here's a quick shortcut. I am going to run out of time in this lesson before I get to do all the shapes I wanted. But 2 divided by 5 is giving 0.4 in the calculator. So shortcut, 1.5 divided by 3.75 equals 0.4. So yeah, that is a bit of a shortcut, but I like not having to use shortcuts, and I like being able to do things on pencil and paper that are easier and faster with the calculator, because I want that feeling of power of being able to do it. So that's it for my rectangles. Let's do some other easy shapes. Squares. Squares are kind of cool with similarity. So let's get into that. Squares are convenient for me to make up questions, and I'll explain why. First, I'm going to draw a square. Wait. I'm going to draw a square that has side lengths of 15 inches. So that's fairly easy to do. Just trying to make nice perpendicular sides. All 4 sides are going to be 15 inches long. Where's my 15? There it is. Finish this. 15-inch sides. And I guess I'll label 2 of them, and I'll label my right angles so that we can see, yes, this is a square with 15-inch sides. Now my second square, I'm not going to give any of the side lengths, so I'm just going to draw it without saying how long these are. There, how's that? Okay, and I'm going to say this is my new, and this is my original. I didn't give any side length. I want to give the scale factor. There, now I have everything I need to know. Okay, now did I say these two squares are similar? Remember, I say that. It's a lot of these problems you really should say in the text with the problem, you say it somehow, that the two shapes are similar. But the cool thing about squares, and yes, I should show evidence, this is actually a square. So here's some of the evidence. In fact, I'll even label it square, just in case someone thought it's a rectangle that's close to being a square. No, it's a square. But I didn't say they're similar, because I don't have to. Because the cool thing about squares is all squares are similar. No matter what size they are, they're all similar. With rectangles, you can have two rectangles that are both rectangles, but they're not similar. It happens quite a lot. With squares, if they're both squares, they're similar. It's cool. So that sort of gives us a little difference in how we ask the question and how we answer the question. It's just a difference in understanding what we need to do. Okay, so the scale factor, I can use it in a proportion. My new is going on top. My new is smaller than my original, and every time my new is smaller than the original, I get a scale factor that is a number less than 1. We are noticing that. If new's on top, if the new is on top, original is on the bottom, that will happen. And I am going to finish my proportion. The side length of this square is 15, and that's the original, so it's going on the bottom, and I can put an x on the top and cross multiply. And I quickly find out that my new square has side lengths of 10 inches. Done. If I want the perimeter, well, the square's perimeter is kind of easy as well, right? The perimeter here is going to be 60. 4 times 15 is 60. Well, we know the perimeter of this is going to be 40. 4 times 10 is equal to 40. But of course, we can also use similarity and a scale factor to figure that out. Even though we already figured it out, 15, 15, 15, 15 is 60. 3x equals 3 times 60. 3x equals 180. Wait, write down your scale factor correctly, Doug. It's 2/3. So 3x is equal to 2 times 60, which is 120. Let's fix this up. Silly mistake. Cancel, cancel. X is equal to 120 divided by 3, which is 40. That's the answer we knew we were going to get. 40 inches is the perimeter of the second square. So yes, squares are fast. Fast to do. Now I'm going to draw two squares without saying, well, draw two squares, and I'm going to give the, I'll give the perimeter of both. Yeah, that's fun. And then we'll figure out the scale factor. I want to do this quickly so that I have time for more examples. How about a nice big original? So I'm going to do that. Nice big original. That's a little bit sloppy, the drawing up there. Squares. Square angles on the corners. This is my original. And its perimeter is 80 inches. And now I'm going to draw another square. I'm going to use my little shortcut. And I'm going to take advantage of the fact that we know it doesn't matter the orientation. So I'm going to draw this square so that it's twirled like this. It's a square. I'm going to mark the corners. I'll even say square. I want to. I'll even say this is a square. I need more chalk though. Okay, and the perimeter of this one happens to be 26 inches. I know that because I use that wooden square thing all the time. Okay, so what's the scale factor? The scale factor is equal to new over original, which is 26 over 80. It's not necessarily the most easily reduced or beautifully reduced scale factor ever, but that doesn't matter. So the greatest common factor between 26 and 80 is just 2. So all I can do to reduce is to divide both top and bottom by 2, and that means 13 40ths. 13 40ths is the square factor. That's reduced. It's the reduced scale factor, not square factor, scale factor for these two squares. And it just happened that way that you didn't get the most beautiful looking number because you don't have to. Because I knew this was 20 inches on a side when I drew it, but this thing was sort of dictated by the size this is, and I just happened to know that it's 6.5 inches on each side. So those are the numbers I got. So that's the scale factor I have, and if I needed to use it to solve for anything, I'd be able to do it. All squares are similar. I didn't even have to say these two squares are similar. I did have to say they're squares. I did have to give you enough evidence to realize they're squares so that you can apply the knowledge that all squares are similar. Nearly out of time, but I do have time to do one more cool shape, which is just as cool as the square. Okay, here's one. I think the students may have seen this particular circle drawing tool before. Okay, and I'm going to mark my center. I don't remember the dog, she's coughing. I don't remember the size of this, but I'll measure it. And now I have to quickly get another round thing, and it's not here, so I'll be right back. Hate that disappearing from camera like that, but sometimes you just have to do it. So yes, this thing that you use to put over food in the microwave so that the food doesn't explode all over the microwave. Marking my center. And we need to know the scale factor of these two circles. Wait, are the two circles similar? Did I say so? I don't have to. Like the squares, all squares are similar, all circles are similar. If they're both circles and these two are, then they're similar. So how long is this? This is 3 inches. How long is this radius? This is 5 inches. Okay, so we already know everything that we need to know. We know all sorts of things about circles, so which is the new, which is the original? For a change, I'm going to say my original is over here. Remember? Doesn't have to always be on the right. The new can be on the left. So new over original is 3 over 5. I have a scale factor which is already reduced. So 3/5 is the scale factor. The problem with circles is, okay, what can I use it to find? Unlike the triangles and the rectangles that have all these side lengths that you can calculate, with the circle, well, it's pretty, the only straight line I see is the radius. The only distance in the circle is the radius? No, diameter. But do we want to use the scale factor to figure out a diameter when we know 3 times 2 is 6, there's the diameter, 5 times 2 is 10, there's the diameter. Okay, so the diameter is too easy. What about the circumference? Yes, we have just about enough time to do that. So the circumference of my original is 2 pi r, which is going to be 2 times 3.14 times 5. Should show it like that, I guess, which is 31.4 inches. There, we found our circumference. Now, of course, we can find the circumference of this one the same way, but instead we want to use a scale factor. So 3 over 5 is equal to, now the 31.4 inches is my original, so that goes on the bottom. I have to be careful because first time that I put the original over on the right side, I don't want to get mixed up. X goes here. 5x equals 3 times 31.4. 5x equals 94.2. 3 times 30 is 90 plus 3. Yep. And now I want to divide both sides by 5. This isn't going to fit very easily. These cancel. So my final answer, x is going to be equal to 94.2 divided by 5. Can I do that in my head? 18.84. And of course we could use the circumference formula if we want to find the circumference of this. And I won't be surprised if it's 18.84, but I'm still going to take advantage of a couple of seconds of time I don't really have to double check this. 94.2 divided by 5. Yes, it's 18.84. So, the next time you see a dog that looks just like this one, and except it's bigger or even maybe smaller, I guess what you need to do is figure out the scale factor, and I guess also figure out which is the new and which is the original. But from Mocha, I'd like to say goodbye. Oh, see, she's not comfortable. There. Okay, now say goodbye. And I am happy to have taught you math as usual. Thank you very much. Okay, you're going down there again. As usual, it has been a pleasure, and I will see you next time.